This is lecture 12. In last two lectures, we have discussed state space analysis, and we have seen how to find the solution of state equation. Today, we will be discussing two important concepts of state space analysis. So those are controllability and observability. That is controllability and observability. So these two concepts indicate the structural property of the realized system. So let us first discuss what is controllability. So controllability indicates that if you have any state, suppose you have a state here, so at time t equal to t0, then if there exists an input so that the state can be steered, can be derived in any position within a finite time. So that is say xtf. So here this tf greater or equal to t0. So this is a finite time. So within a finite time, if there exists an input so that a state can be steered from its initial point to any point in the state space. So suppose you have, this is another one, so that is tf dash. So it can be steered from here so that there exists one input. Then that state is called controllable. So now for a system, if all the states are controllable, then we say that the system is completely controllable. So controllability means there exists an input. So in case of controller design, before designing a controller, we need to ensure that the system is controllable. So that means if the system is controllable, we can assure that there always exists a controller. That means there exists an control input so that the state can be steered from one point to any arbitrary point within a finite time. So let us write that formal definition of controllability. The state xt is said to be controllable at t equal to t0, that is that initial point, if there exists a piecewise continuous So piecewise continuous signal means, suppose this is that t and here you have that ut. So piecewise continuous means, so you may have a control input like this one. That means even if there is some discontinuity here, discontinuity at that point or at that point, so the from this point to that point it is continuous, but there is some discontinuity. So there may be some finite discontinuous point. So then that signal is called that piecewise continuous. So that means whenever we have a signal, control input signal, so we may allow some discontinuous point, but this would be that finite discontinuous point. So this is actually that piecewise continuous signal. So piecewise continuous input ut that will drive the state to any, so that is important, to any final state xtf for a finite time, tf greater or equal to 0. That is also an important term, that is within a finite time, because it might happen that there exists one input but it takes infinite time, so it is not controllable. So few things you need to remember. That means a state is said to be controllable if there exists a piecewise continuous input ut such that a state can be steered or can be driven from one point to any point within a finite time. So this is called that controllable. The system is controllable. So now we will see how to test that whether the given state space realization is a controllable realization or not. So it is very easy to test. Whenever a system is described as x dot equal to ax plus bu and y equal to cx plus du. So suppose let a system, of course we are discussing that LTI linear time invariant system, let a system be described as say x dot t equal to axt plus but with initial condition is 0 and yt equal to cxt dt dut. So in case of controllability, that output equation is not important. Basically that system equation is important, because the system matrix A and input matrix B will decide whether the system is controllable or not. So the pair AB, so that means that system matrix A and input matrix B is controllable if and only if, so this is necessary and sufficient condition, if and only if there is a matrix, so we need to form a matrix like this: S equal to B, AB, A square B, like that, A to the power n minus B is of rank n. What is that? So whenever a system description is given in state space, that means x dot equal to ax plus bu, y equal to cx plus du, and we are interested in to see whether the system is controllable or not. So we have seen what is the definition of controllability. That means that state can be derived from any, so from initial point to any point within that state space within a finite time, and if there exists an input, then that state is said to be that controllable. Now for a system, if all the states are controllable, then it is called completely controllable. So now let us see, whenever a system is described by its state equation like this, so then the controllability depends on the two matrices. One is that system matrix, another one is that input matrix. So then that pair AB is said to be controllable if and only if we form a matrix like this, we'll see it later by an example. What is that matrix? So this particular matrix is called that controllability matrix. Controllability matrix. So we need to form the controllability matrix and check whether the rank of this matrix is equal to n or not. N is that number of state variables. So here that xt belongs to r to the power n. So that means n is the number of state variables. So if that system has n number of state variables, then the system is said to be controllable. So that means you know that n should be n cross n matrix, b should be n cross r matrix if r equal to u belongs to r cross 1. That means r number of inputs are there. So here x, the dimension is n cross 1. So then if there are a number of state variables, and if you form this controllability matrix, then that pair AB is said to be controllable if the rank of this matrix equal to n. So that is actually the testing criteria. So let us see some example. So here I am taking a simple example, say x1 dot x2 dot. As I have just pointed now that controllability depends on A and B matrices. So that's why I am not writing that output equation. I am just writing only system equation. So that is, so this is your A matrix and this is your B matrix. So now we are interested in to see whether the system is controllable or not. So for controllability, immediately we need to form this controllability matrix. So that is B and AB. So controllability matrix S, first you write B. So B is 1, 0, and now AB. So A into B. A, that is minus 1, 0, 0 minus 2, and B is 1, 0. So you will get AB, that is minus 1. Just you do that matrix multiplication, and here you will get that 0. So AB means another column. So here that is minus 1, 0. So I hope now it is clear. That means B, if it is a single input system, then you have one column, B matrix. Then AB means another column, A square B means another column. So that means if you write those columns side by side, then it forms a matrix which is called controllability matrix. In case of single input, single output system, that controllability matrix becomes square, but in case of multi-input, multi-output systems, it is not a square matrix. But in any way, in case of multi-input, multi-output system, the rank of this controllability matrix should be equal to n, that is the row rank. So what is the rank? So rank of this matrix, rank of S equal to 1. So it is a rank deficient matrix. So here how many state variables are there? So 2 state variables. You can see here 2 state variables. So you have 2 state variables, that means n equal to 2, but you can see here the rank of S equal to 1. So that means it is not equal to n. So what we can conclude? We can conclude that it is not controllable. So this particular realization is not controllable. So it would be very much clear if we draw the state diagram. So you have two state equations. So from here you can see that that is x1 dot. You have that x1 dot equal to minus x1 plus u. This is one state equation. Another equation is x2 dot equal to minus 2x2. So if we just realize, if we draw the state diagram, so this is called that state diagram. You have two integrators. So here you have that x1 dot, you have x1, and you have another state variable that is x2, and here you have x2. So the first state equation, that is x1 dot equal to minus x1. So here you have, this is minus x1 plus u. That means u is entering here plus u. And what is x2 dot? x2 dot equal to minus 2x2. That is minus 2 gain 2x2. So this is that state diagram. So from this state diagram, you can understand that this control input is only driving this state. But anyway, that x2 is not connected. So here you can see that x2 state is not connected to u. So that means if you were interested to drive this x2 from any point to other points, there is no control input because u is not connected to this x2. So from this state diagram, it is clear that this realization is not controllable. I hope now it is clear. That means what is that controllability, because it is actually the structural properties. And from this structure you can understand, that means if you have a state space description like this, then applying that mathematical testing criteria, you can directly say that as the rank is equal to 1, it is not 2 because two state variables are there, so it is not controllable. And the same thing also you can understand if you draw the state diagram, and in the state diagram you can see that the one state is not connected to this control input, so you cannot drive this state x2 from any initial condition to any arbitrary point. So that means that x2 does not depend on that control input, so you cannot do that. So that's why the system is not controllable. So let us see one more example here. So the same example, if we just modify a little bit, then what happens? Say suppose we have a state space description like that, minus 1, 0, 1, minus 2, x1 and x2 and u. So let us first try to understand whether this system is controllable or not. So for controllability, we have that A matrix and this is that B matrix. So let us first see what is that state diagram. So the first equation, we are getting that x1 dot equal to minus x1 plus u, and that second state equation we are getting that x2 dot equal to x1 minus 2x2. So now if we draw the state diagram, so we have that first state, we are taking integration, so that x1 dot, and here you have that another state, that is x2 dot, here you have that x2. So the first equation is x1 dot equal to, this is minus here, and we have that control input u, and what is x2? x2 equal to, you can see here that x1 is connected to this x2, and then we have this one. So x2 dot, here you can see that x2 dot equal to x1 minus 2x2 and x1 dot equal to this. So now here you can see that this is that control input. So it can drive this x1 because it is directly connected to this x1, and here just if you see the other state diagram, so in this case that x2 actually was isolated, but here in this case you can see that you can drive this x2 via this x1, because if you want to control this x2, so first you need to control x1 and then it would be transmitted to that x2 state. So that means x2 state, it is not directly connected to you, but it is connected via x1. So that means there exists a connection with that control input. So from this state diagram, it is clear that it should be the controllable realization. So let us see if we just test via that controllability matrix. So the controllability matrix is that B, the controllability matrix is B, A, B. So let us see, that is S equal to B, A, B. What is A, B? So A matrix is this one. So that means A is -1, 0, 1, -2, and 1, 0. So then that would be equal to -1, and this one equal to 1. So you may ask one question, that means how many terms you will be taking here? How many terms? Because it is B, A, B, A square B, like that. So you can see here n, a to the power n minus 1, as here n equal to 2. So basically we will be taking only the second terms. If it is 3, we will be going up to third terms. So here you will have AB equal to -1, 1. So B matrix we have, that is 1, 0. So then if we write it, B is 1, 0 and AB equal to -1, 1. So what is that rank? So rank of S equal to 2. So here the number of state variables is 2 and the rank is 2. So it is controllable. So it is controllable. So here we have just discussed two examples. So one example is not controllable, and that we have understood from state diagram as well. And here this is another example which is controllable, and we can see here that two states are connected to that control input, so that we can drive those states from any initial conditions to any arbitrary point in the state space within a finite time. So let us see that another concept which is called that observability. So observability, this is also one structural property of the state space realization. And here if we have say suppose this is T0 and this is TF, and if we know the control input UT in this particular time range, as well as if we know the output of that system in that time range, along with we have that information of those matrices. That means if we know the state space matrices of the system, that is A, B, C, D, along with if we know UT and output, then if we can calculate the value of that state at t0, then the system is said to be observable. Let me repeat once again. So in a time interval, if we know control input and if we know the output of that system, along with if we have the knowledge of those state system matrices A, B, C, D, state space matrices, then if we are able to calculate the state at t0, then this system is said to be observable. So this is actually a structural property, and it says whether we can calculate any state variable at the initial condition or not. So let us see the formal definition. The state x0, the state xt0 is said to be observable, if given any input ut, there exists a finite time tf greater or equal to t0. Here we have seen that is tf, such that the knowledge of ut, as I have pointed out, if you know that control input ut for in that interval, if you know the input matrices, all state space matrices C and D, if you know those things, and the output yt for, so in that same interval, if you know that input and output are sufficient to determine xt0. So the concept is, if you know that control input, that means the state xt0 is said to be observable if given any input. So that means if you know that input, there exists a finite time such that the knowledge of ut for this time interval and matrices A, B, C, D, if you know those matrices and output also in that time interval, then these data are sufficient to determine xt0, then it is said to be observable. So how it would be effective? So that means with those given data, if you can calculate xt0, then you know that state xt equal to e to the power at xt, say t minus t0 xt0, you know that one. So if you can calculate in any time interval that xt0, and as you know t, so then easily you can calculate xt, because this is that state transition matrix, and this is that, if you can calculate xt0 any for any time, finite time, so you can calculate that state xt. So this is actually that concept. That means for a given state space realization, if you can calculate that xt0 for given ut, yt and abcd matrices in that time interval, that t0 to tf, then if you can calculate xt0, then the system is said to be observable. similar to controllability. So there is a matrix which is called that observability matrix, and of course the observability, you will see that it depends on A matrix and C matrix. So in case of controllability, it depends on A and B, system matrix and input matrix. And in case of observability, it depends on system matrix and output matrix. So that observability matrix is C, CA, CA square, like that. So CA to the power n minus 1. So you need to form this observability matrix is of rank n. So n is that number of state variables, like that controllability. N is the number of state variables. So in case of observability, what you need to do, say one state space realization is given, and for testing observability, you need to know that A matrix and C matrix. Then you form this observability matrix and find the rank. If that rank is equal to n, then the system is said to be completely observable. So let us see some examples. So one example is here. Suppose you have that state space realization x1 x2 dot equal to that -2 0 0 -1, and x1 x2, and then 3 1 u, and here y equal to 1 0 x1 x2. So in case of controllability, actually we have seen that state should be connected either directly or indirectly to that control input. And in case of observability, you need to see whether the effect of a state is reflected in the output or not. That means if the state is not in any way connected to that output, so directly or indirectly, then that state would not be observable, because just by looking at that output, you cannot calculate that state as it is not in any way connected to that output. So let us just draw that state diagram in this case. So then the first state equation is -2x1 plus 3u, and second equation is x2 dot equal to -x2 plus u, and that output equation equal to x1. So now if you draw that state diagram, what do you get? So here you have two state variables x1 x2, and this is that integrator x2 dot equal to x2. So now x1 dot, so here we can see that there is a gain 3 and input entering here, that is u plus, and here this is minus, so the gain is say 2, and first equation is satisfied. And then the second one is x2 dot here, that is -x2, and this u is connected here. So both the states are directly connected to that input, but if you look at that output equation, so this is only that output. So now you can see that this x2 is not connected to y. So that means this effect of y x2 is not reflected in that output. So then just by looking at u and y, and if you know that ABCD matrices, you won't be able to calculate this x2. So that means from this state diagram, it is clear that this particular realization would not be observable. So let us see, if you just find that observability matrix here, so what will you get? That observability matrix is C, CA, because here n equal to 2, so that means we will just go up to second term, C, CA. So then what is C? C is 1 0, and what is CA? So let us calculate first CA. CA, so that is 1 0, and A matrix is your -2 0 0 -1, -2 0 0 -1. So then you have that -2, and you have -2, and then you have 0. So it is 1 cross 2, and here this is 2 cross 2, so that should be 1 cross 2 matrix. So then if we write what is your C matrix, so C is equal to 1 0. So first you write C, that is 1 0, and then CA that is -2 0. So what is that rank? So rank of V equal to 1. So you can see that as it has two states here, but its rank equal to 1, so it is not observable. So this is that structural property of that state equations. That means whether it is controllable or observable, and whenever all states are observable, then we say that it is completely observable. So now we can see one simple example where we can understand that some state may be controllable but may not be observable, but some state may be observable but they are not controllable. Let us take one simple example, and from there we will understand this structural property. That is, suppose you have 4 states, that is x1 dot, x2 dot, x3 dot, and x4 dot. So this is that state description, that is -1 0 0 0 0 -2 0 0 -3 0 and -4. So you have x1 x2 x3 x4. Now that input matrix is 1 1 0 0. Suppose you have this description, and y equal to 1 0 1 0. Then suppose this is x1 x2 x3 x4. So now first let us we'll just understand that controllability and observability from state diagram. So if we just consider that first state equation, so there are 4 state equations, so that means we need 4 integrators. We need 4 integrators, 1 2 3 and 4. So we need 4 integrators here. So this is x1 dot, so this is x1. Here you have that x2 dot, here x2, here x3 dot, you have x3, and x4 dot, here you have x4. So there are 4 integrators, and here you can see that x1 dot equal to -x1 plus u. So -x1 plus u, so that means here this is -x1 plus u means control input is connected here. control input is connected here. So now if you just look at the second state equation, so x2 dot equal to minus 2x2 plus u. So x2 dot equal to minus 2x2. So that means here 2 is there and this is minus 2x2 plus u. That means u is also connected here. So now look at the third equation. Third equation is x3 dot equal to minus 3x3, but there is no u. So minus 3x3, that means here minus 3x3, that means 3 minus, but there is no input here, and x4 dot, that is equal to only minus 4x4. So this is minus x. So 4 and minus. So these are all the state equations. So now we see what is that output equation, y equal to x1 plus x3. So y equal to x1 plus x3. So that means if we have y here, then x1 plus x3. So this is that state diagram corresponding to this state equation. So here you can see that this is that input, this is that input, and this is that output. And in output only x1 and x3 are reflected, but x2 and x4 are not reflected there. And here you can see that if you just look at this particular state, it is just isolated. That means control input is also not connected, as well as it is not reflected at output. So this particular state is not controllable. So this particular state is not controllable and not observable. So this state, as it is isolated, it cannot be controlled or cannot be observed. But what happens for this particular state? You can see here that it is not anyway connected to that control input, either directly or indirectly. So it is not controllable, but you can see that output of, that means this state is reflected at output. So that means not controllable but observable. So it can be observed there. And what about this state? So this state, you can see that control input is directly connected to this state. So that means it is controllable but not observable. And this state, you can see that it is connected to that control input, as well as it is reflected, at output. So that means this particular state is controllable and observable. So this particular example is very interesting, and here you can see that if you have a state space description like that, it has 4 states, and just from this state diagram we can understand that 4 states are actually 4 different types. So the first state is controllable and observable, and the second state is controllable because that control input is connected directly to this particular state, but you know it is not reflected at output. So it is not reflected at output because this channel is broken. So that's why that controllable but not observable. And here you can see that This is observable but not controllable, as the control input is not connected, and this state is completely isolated, so it is not controllable and observable. So one interesting thing you can note here, that means whenever you will be finding the transfer function from input to output, you can see that in the transfer function only that state would appear which is actually controllable and observable. That means even if it is a fourth order system, because four state variables are there, if you find the transfer function, only this particular mode would appear in the transfer function. That means if you find that ys by us, you will see that the transfer function would come s plus 1, because this is that pole. You can see here, this is that mode, and this particular mode is here. That means this is that state which is controllable and observable, and in the transfer function only the controllable and observable mode appears. The other modes, if you look at here, one mode is -2, another one is -3, another one is -4. So minus because the negative feedback is there, you can see, which is reflected here as well, that -2, -3 and -4. That means if you find the eigenvalues of that matrix, the eigenvalues of, as it is a diagonal matrix, so its eigenvalues would be -1, -2, -3 and -4. And these are the four modes of this particular system, or you can say that these are the four poles of this particular system. So poles of that systems are actually that eigenvalues of that matrix, A matrix, and out of those four poles, only one pole is controllable and observable. And if you find the transfer function, so how will you be finding transfer function? Already we have discussed. If you just write ys equal to c into si minus a inverse b, because here D matrix is 0, so US. So I suggest you all to do this one. Whenever your C matrix is this, B matrix is this, A matrix is this. So if you just find the transfer function, you will see that your transfer function would come only 1 by S plus 1. So as you know that this order of the transfer function, so here it is coming order 1, but you can see that here the order is 4, as you have 4 state variables. Then where the other 3 state variables have gone, so those state variables or modes or poles are not appearing in the transfer function. The reason is they are not controllable and observable. So this -2 mode is controllable but not observable. This -3 mode not controllable but observable, and -4 mode is not controllable as well as not observable. So that's why these three modes are not appearing in transfer function. So in transfer function only that mode appears which is controllable and observable. So I suggest you all to solve some problems, and then I think it would be clear. So now let us see what is that realization problem. So realization. So this is very important. So realization means transfer function. So realization means transfer function to state space. So this particular problem is called that realization problem. That means a transfer function is given. So a transfer function is given, GS is given, a GS is given. You need to find what is ABCD, A, B, C and D. So this particular problem is called that realization problem. So whenever you are asked to realize asked to solve a realization problem, it means a transfer function is given or transfer function matrix is given. You need to find what are the state space matrices. So before starting that realization problem, so let us discuss one important fact, because we have already discussed that means improper transfer function cannot be realized. So that means if I give you an improper transfer function, you cannot have any A, B, C, D matrices. Why? The reason is, as we all know, that GS, the transfer function GS, equal to C into SI minus A inverse B plus D. So now if you look at this particular term, so we have seen it in last two lectures that SI minus A inverse, this is equal to actually adjoint of SI minus A divided by the determinant of SI minus A. That is the formula of this inverse. If you forget this one, so I suggest you all to see the linear algebra book. So now this is actually SI minus A inverse. So now you can see that the C matrix, B matrix and D matrices, they all are constant matrices. So now what would be the degree of the determinant of SI minus A? Suppose A is a matrix, that is the system matrix whose dimension is n cross n. So if you find the determinant of SI minus A, so its degree would be equal to n, degree is n. So I think you can understand if we take a simple example here. So suppose A is a 2 cross 2 matrix, that is say suppose 1 2 0 3 is a 2 cross 2 matrix. So now if you find determinant of SI minus A, so in this case the determinant of that S00S, this is that SI minus A is 1 2 0 3. So then you have determinant that is SI minus 1 minus 2, then this is 0, this is SI minus 3. So you will get SI minus 1, then SI minus 3, then this one, because minus 2 and 0, that would be 0. So if you just multiply that one, it would be a square, then minus 4s plus 3. So then you can see that the degree of this determinant of degree of this one means, so if you find the determinant of SI minus A, you have that polynomial and its polynomial degree is equal to, here you can see the degree is 2. So if you have one n cross n matrix, its degree would be equal to n. Here your matrix is 2 cross 2, that's why its degree is coming 2. And now what is adjoint of that matrix? So adjoint of this SI minus A. So adjoint of SI minus A means SI minus A. So this is actually your SI minus A. So whenever you find that adjoint, so you need to find that cofactors. So that means here for with respect to this term, if you just remove that row and column, so you have that SI minus 3. Similarly, if you want to find the cofactors of that SI minus 3, so that means if you just remove this particular row and column, you have SI minus 1. So from here you can see that in case of adjoint of SI minus A, each element would be one constant element, or it is that one is function of S. Now, what would be the maximum degree of those elements? So in this particular case, the maximum degree here, degree equal to 1. So anyway, that means whenever you find the adjoint of that Si minus A, adjoint of Si minus A, the element of adjoint of Si minus A, its degree is always less than the degree of n. So in that case, what you can have, whenever you find Si minus A inverse, as this is equal to adjoint of Si minus A by determinant of this, and its degree is n, and in the numerator its degree is always less than n. So that means if you just consider only that term, you have some matrix where each element is a rational element, and those rational element would be strictly proper. That means the denominator degree would be greater than the numerator degree. And if there is a D term, D is a constant matrix, then you can see that the degree of this GS, numerator degree of that GS, would never exceed the degree of the denominator's degree. That means the degree of the numerator would never exceed the degree of denominator degree. So that thing you can see by one example, and from this expression and from this argument it is clear that if you have one improper transfer function, improper means, so improper transfer function, improper, we have already discussed, improper transfer function means numerator numerator's degree is greater than denominator degree. Degree is greater than denominator degree. So improper transfer function means numerator's degree is greater than denominator degree, and from this particular argument we have seen that if the transfer function, as the transfer function G is equal to C into Si minus A inverse B plus D, we cannot have any A, B, C, D matrices such that the numerator degree would be greater than the denominator degree. That means improper transfer function, cannot be realized in this form. So that means here, let me just write this one, since Si minus A inverse is equal to adjoint of Si minus A divided by determinant of Si minus A. So that is actually that formula. The degree of the element of adjoint of Si minus A is less than the degree of determinant of Si minus A. So that means in this particular case what we have discussed now, that means its degree would be always less than the degree of this. So that means if I give you an improper transfer function where the degree would, numerator's degree is greater than the denominator's degree, with this particular structure you cannot realize that transfer function. So that's why the improper transfer function cannot be realized. As we have seen, the realization means a transfer function is given, you need to find state space matrices. But from here we have seen that if I give you one improper transfer function, never you can have one A, B, C, D matrices such that this particular relationship holds. So that's why that improper transfer function cannot be realized. So an improper transfer function cannot be realized. So today what we have seen, we have started with two structural properties, that is that controllability and observability, and we have seen the definition as well as we have understood that structural properties via some examples, and we have drawn that state diagram from where those structural properties are very clear, and we have taken the definition of observability, and finally we take one example where we have shown that uh, a state may be controllable, observable, may be controllable and not observable, or maybe not controllable but observable, like this. So there are various combinations, 4 combinations, and then we have discussed what is that realization problem. So realization problem means a transfer function is given, then we need to find what are the state space matrices A, B, C, D, and here we have discussed that any improper transfer function cannot be realized. That means if an improper transfer function is given, there does not exist any A, B, C, D matrices, so that this particular relationship, the transfer function relationship, holds. So next day we will be discussing that state space realization, and we'll be just discussing how to linearize one state space model. Thank you.